All right, we are going to get started. Thank you everyone for joining us. Day 2 for our MIBI processing session. Going to okay, so this session is very MIBI specific. So all the other parts of the workshop that we covered so far, and the ones in subsequent sessions will be sort of more generally about multiplex imaging analysis. This one is highly tailored to the initial low-level processing of MIBI data. Everything that we're going to talk about in this session is publicly available as part of the Toffee GitHub. So this is where we put all of the sort of MIBI specific run setup, acquisition, tweaking, and image processing tools that work specifically for the commercial instruments. There's a nice README that walks you through it. We've sort of laid out how you can install Toffee directly on the CAC computers that control the MIBI, and we've tried to streamline this process as much as possible so that any IMPACT customer can get this running in a reasonable manner. So I'm going to give you a brief overview of sort of what the Toffee workflow looks like. In general, before we dive into the individual talks in this session, going through sort of the key parts. The first part is setting up Toffee. So there's a notebook that will walk you through basically how to install it, how to configure it. There's some instrument-specific settings. And the next thing is that you shouldn't do anything else if you're not acquiring a cohort, basically. So everything we talk about today is going to be the image processing we do when acquiring large cohorts. If you are just doing regular day-to-day QC runs, the amount of time and energy that this processing pipeline takes is really not worth it. As Hadeesha mentioned, when you're just QCing antibodies or looking at if they work or not, the eyeball test is like more than good enough. And so the purpose of the Toffee pipeline is once you have image data that is ready to be analyzed as part of a publication, then you're going to go through the effort of cleaning up all these sources of noise and whatever. But if all you need to figure out is sort of a yes or no of did my experiment work, and then that data is not actually going to be analyzed, this is not needed. And so this session kind of pairs perfectly with the second session from yesterday about cohort acquisition consideration, and is not super relevant for the first session, but just general antibody QC integration. So if you are ready to acquire cohorts, that's great. The first step in the pipeline is how do you want to set up your runs. And so Hadeesha alluded to this yesterday in his acquiring FOVs for your cohort. There's basically 2 notebooks. One of them is designed for PMAs, and it'll guide you through some sanity checks basically to make sure that you named all your cores correctly, that they're in the right spot. And then it'll randomize the acquisition order so that there's no confounding between potential batch effects of the instrument and the way in which your TMA was laid out. The other notebook is for tiled runs. So if you're going to stitch a bunch of images together to get something like a 1600 by 1600 or 3200 by 3200 image, that notebook will automate that process so you're not yourself trying to piece together the jigsaw puzzle. After that, there's sort of a fork in the road. And there's 2 ways that you can do the QC and initial processing steps of the pipeline. The first is just do everything automatically. So we have a notebook that will, in real time, as the image data is generated, run it through these sort of key processing steps. Just extracting the tips, generating QC metrics, checking that the pulses look good, all this stuff. That can just happen automatically, or you can run the notebooks one by one. And so, when you're first getting familiar with it, if you care about the underlying details, you can walk through each notebook yourself. Once you're more comfortable, or if you're just happy with all the defaults, you can run this automatic processing notebook. The benefits of this automatic processing is that because each individual step doesn't take that long as a fraction of the amount of time it takes to acquire the data. But if you've been doing a long run, it could be that in some there actually is a fair amount of processing time. And so if you can do that processing after each image gets generated, then by the time your run is done, the processing is also done. If you wait to do it after the fact, you could have it's not the end of the world, but it's somewhere between 2 to 4 hours of processing to actually look at your data before you can go on to the next experiment. And so once you're sort of comfortable with how that works, This can happen simultaneously, so that as soon as your run is done, you're ready to set up the next. After that, there's some post-processing steps. The first one is the Rosetta pipeline, which we're going to talk about today. If we'll go into more details, this is sort of our image subtraction, background correction, denoising approach. And the second is image normalization. So this is how we control for potential differences in sensitivity at various points of the run and remove these effects so that a positive signal from the first image looks the same intensity as the positive signal in the last image. And then finally, there's some sort of helper scripts that just reorganize all your data. You could have 15 different runs that got split up that have restart 3 and all this stuff in there. It basically consolidates everything into an image data folder that is ready to be analyzed either by ARC analysis, which we'll talk about later, or any other image processing suite. Okay, so what are we going to talk about specifically in this session? First, we'll be hearing about Rosetta image compensation from Erin in our lab. This is sort of our new approach that abstracts and automates a lot of the previously painful parts of correcting batch effects and sources of noise in our image data. We'll then hear from Hadeesha sort of a more applied example. So the first talk is like, how does Rosetta work and why did we come up with it? The second one is how do you get Rosetta working on your data and what changes might you have to make and how do you adjust the parameters to get the optimal results. Finally, you'll hear from me about the steps we've taken for image normalization and in general, how we have come up with a new way to assess the sensitivity of the MIBI instrument, which we've used in a couple different steps in our pipeline throughout. The real goal here is to understand the processing pipeline, as I mentioned, for MIBI cohorts. So none of this stuff needs to be done if you are just doing the day-to-day image acquisition stuff. Looking at the results of your experiments by eye, this is not anything that you feel like, oh, I need to clean it up in order to see the answer. Probably that's your answer right there, and it's not actually cleaning up data to move forward with. This is really to enable you to do quantitative analysis of the images without having to, in your head, sort of integrate around potential source noise. As we talked about before, there's also a number of pre-recorded talks that sort of go into more technical details about various steps in this pipeline. We have a talking installation notebook, doing the tiled runs, all of the sort of QC metrics and extraction and the automated versus the manual workflow. We have notebooks talking about how you set those things up. And then also the final notebook, we also have a little demo of. Okay, so with that, I will turn it over to virtual Erin, who has pre-recorded her talk because she is somewhere without any internet service at all. So hopefully this will work.
Step we must take when processing our newly collected imaging data, which is known as Rosetta image compensation. And so to begin, I'm showing you here 3 examples of raw MIBI top data that has undergone no processing except for basic data extraction. On the left is CD45, a membrane marker that delineates immune cells. In the middle is calprotectin, which stains neutrophils. And on the right is CD3 epsilon, a membrane marker that labels T cells. Now, as you can probably appreciate in each of these images, in addition to our true signal, we can see that there are various sources of contaminating background and noise. Now, before we can proceed with processing our data downstream, we must be able to account for and remove all of these contaminating signals from our imaging data so they don't introduce artifacts when we begin to analyze our single cell data downstream of low-level processing. And so ideally, we'd move from data that looks like this to images that look like the examples here. Whereas you can see, the vast majority of signal remaining in each of these images is attributable to true biological signal. And the approach that we've developed for achieving this is known as Rosetta compensation. So if you take away anything from today's presentation, it should be 1, that background in MIBI top data is systematic. 2, that previous approaches for performing background subtraction or denoising are not scalable or result in problematic signal attenuation. And to overcome these challenges and take advantage of the fact that background in our data is systematic, we developed an approach known as Rosetta compensation that provides single-step and scalable compensation to clean MIBI top data. And so first, I'm going to walk you through each of the various sources of background or noise you might see in your MIBI top data. The first and most common source of background is that attributable to regions of bare slide. As you're probably familiar at this point, tissues analyzed by MIBI are mounted onto microscope slides that are sputtered in gold. This provides a conductive surface for imaging. However, when we image tissues, especially those that might contain holes or regions of bare slide, such as the example here of human placenta, we can see that in addition to collecting ion signal from the tissue, we're also collecting gold ion signal from these regions of bare slide. What this results in is the presence of background in our mass channels of interest. And so here I'm showing that same human placenta, only now I'm showing staining for smooth muscle actin at mass channel 115. In the pre-compensated image, we can appreciate that in addition to our true signal, we also have these regions of background signal that directly co-register with regions of bare slide. Now, when we image these regions during a MIBI TOF run, a tremendous number of gold ions will enter the detector, and this can cause ion pileup or wraparound signal, leading to the presence of these regions of background. Now, ideally, after compensating our data, we would get the resulting image on the right, where you can see that we've largely removed the entirety of this contaminating signal, and the only thing that remains is signal coming from smooth muscle actin itself. Now, the second most prevalent source of background in our data is attributable to organic hydrocarbons, and we often call this noodles. So to break down where our signal is actually coming from in a given mass channel, I'll use the example here of mass channel 165. Now, when it comes to the isotopes that we've conjugated to our antibodies, these isotopes are in fact mass deficient. And what this means is that in the spectra, their signal will appear between mass 164.7 to 165. Now, hydrocarbons, by contrast, appear in the mass proficient window of the spectra due to the presence of hydrogens. So if we have an organic hydrocarbon with a mass of 165, we will actually see this signal in the spectra between 165 to 165.3. Now, ideally, we'd be able to just decouple these signals from each other by only taking data within the mass deficient window of the spectra. However, in order to achieve high throughput and sensitivity with MIBI, this comes at the cost of decreased mass resolution. And so what this means is that often in our spectra, we'll just see the presence of a single peak at each of our masses, and this peak will have contributions attributable to both our isotopes of interest and organic hydrocarbons. And I'm showing here an example of what that signal might look like in your imaging data, where we can see in this image that we're finding organic signal deposited along the topography of the tissue. And it's this striated appearance of the organic signal that gives it its name of noodles. And so bare slide and organic background are going to be the two primary and predominant sources of background you'll see in your imaging data. However, there are two other more minor contributions that must be accounted for when compensating our data. The first is signal that comes from isotopic impurities. When we conjugate our antibodies to metal, we use metal stocks that are isotope enriched for specific masses. However, these stocks in practice are only about 99% pure. So if we look at the example of 142 neodymium, neodymium itself has isotopes that naturally occur across these 5 different mass channels. However, when we want to conjugate an antibody to 142, we use a stock of neodymium that has been isotope enriched, where you can see here now nearly 99% of the composition of that stock is comprised of the neodymium isotope at 142. However, because we cannot completely purify these isotopes, we can appreciate that we still have what are very minor contributions of the remaining mass isotopes for this particular element. And so using our knowledge of the natural abundance or proportions of these various isotopes, we're able to attribute for these source of impurity when we compensate our data. And it should be noted that in general, these contribute very little background, except in the occasional case where you have very bright signal. However, because these are occurring at a systematic rate, it is still important for us to account for them and remove any contaminating signal that might arise. The last source of background we see in MIBI-TOF data is a similar occurrence to what is observed in CyTOF data, which is known as elemental contamination. This occurs when our ions of interest actually bind to other ions before they hit the detector. And so one example here is what's known as an addict. And so if we go back to our example of 142 neodymium, here an addict will occur when this 142 neodymium ion binds with hydrogen, resulting in a +1 signal at 143. We can also observe the occurrence of oxides, which will occur when that 142 ion in this particular example binds with oxygen, and this will cause a +16 signal at 158. And addicts and oxides will really be the two primary sources of elemental contamination that we observe with MIBI. However, it's important to know that there are other types of elemental contaminations that can occur. And so I'm showing an example here of just one, which is what happens where our isotope of interest binds to a nitrogen ion. 14 signal in this example at 156. Now, the nice things about elemental contamination is that the rate of occurrence for all of these contaminating events has been experimentally determined for the MIBI scope system, which means that we know the exact proportion at which they're happening for each mass channel. And so now that we've walked through the various sources of background, it's important to understand why previous approaches to achieving background subtraction might have limitations that result in problematic processing of MIBI-TOF data sets. So up until this point, we've had two primary approaches to performing background removal. The first was a pipeline developed in our lab known as multiplex ion beam imaging analysis user interface, or MAUI. This is a graphical user interface in which the user can empirically choose various sources of background and then produce a mask of that background signal, which they'll then use to subtract contaminating signal from each of their mass channels of interest. The other approach is IonPath's automatic background filtration that will remove background based on the presence of gold signal in TOF cycles. Now, each of these approaches have limitations. In the case of MAUI, while the background subtraction achieved here is usually quite accurate, sources of background are empirically determined. So this does not take advantage of the fact that we know that contaminating sources of signal or noise are systematically occurring. Furthermore, the user must tune the parameters for this processing on a per image and per channel basis. And so in this respect, this pipeline is not scalable. To give you an example from my own work, in my first study, I collected a cohort of 30 imaging fields. For this reason, while it took a bit of time, tuning the parameters for each of these images and channels was still tractable. However, my current data set comprises 3,000 fields of view. And with a data set of this size, it's simply not feasible to expect customized tuning per image. On the other hand, while IonPath's automatic background filtration is rapid and scalable, we observe that this actually causes very aggressive over-subtraction that will lead to signal attenuation and in some cases, the introduction of false negatives. And so to overcome the limitations of both of these approaches, we developed an approach known as Rosetta compensation. And this approach is actually just a very simple compensation method akin to what is used when processing flow cytometry data. At the heart of this method is the Rosetta matrix, which is a compensation matrix that will perform pixel by pixel compensation in our imaging data. So in this respect, it is a very simple approach. Using this matrix, we can achieve channel by channel compensation for all of the various sources of background I presented to you today, in addition to any other contaminating sources of signal that might arise in your specific case. The pros of this approach is that we can process our data in just a single step. It simultaneously denoises the images, and it's a very scalable approach. And as our lab has started to move into collecting bigger and bigger data sets, this approach has proven to be very successful in cleaning up the data in a manner that is feasible for large cohorts. And so there are really four important underlying principles of the Rosetta matrix. The first is that MIBI data contains almost zero stochastic noise. And in fact, all sources of noise and background are occurring due to real ions hitting the detector. Because of this, we can isolate all contributions of systematic noise based on reference peaks. And true signal and contaminating signal are linearly additive, making this situation apt for a compensation-based subtraction approach. And so the Rosetta matrix itself comprises the various source channels that are causing background or contaminating noise along the rows, and our target channels of interest along the columns. And we populate this matrix with coefficients that will account for the rate at which these various contaminating events are occurring. And at a high level, the clean data for each mass channel will be equivalent to the raw data minus the combination of all of these different sources of contaminating background and noise. To break this down into a very simple example, let's say that I have three masses. Mass A is a mass channel where I have an antibody in my panel, and mass B and C are masses that are causing some source of contaminating background in my mass A channel. In the case of mass B, this contaminating event is occurring at a rate of 10% of the original source signal. And in the case of mass C, this is occurring at a rate of 50% of the source signal. Now, if I consider an example pixel, let's say that for mass A, I have 15 counts, for mass B, I have 10 counts, and for mass C, I have 2 counts. In order to compensate this particular pixel, I would need to take my counts for mass A minus the contributions of contaminating signal for mass B and mass C. And so in this case, that would simply be equal to 15 minus 10% of 10 minus 50% of 2, which would result in a final count of 13 counts for this pixel. And so Rosetta really just scales this operation over every possible contaminating source of background across every single channel. And as I've mentioned previously, when it comes to isotopic impurities and elemental contamination, the coefficients or the rate at which these are occurring are fixed, either due to the natural abundance of different isotopes for a given element or because they've been experimentally determined. In addition to this, we have optimized the parameters for gold or bare slide subtraction such that they shouldn't need to be tuned further. However, it is possible that in your own imaging data, you might find that you wish to modify the subtraction coefficients for organic background. This is because we see that in general, while most other sources of background signal in our MIBI-TOF data is consistent run to run or cohort to cohort, we can often see some variance occurring with the noodle channel. And so in order to remove this signal, we identified while developing the Rosetta matrix a mass channel between 117 to 125 that really picks up a nice representation of this organic signal. And if I zoom in on an example here, you can see once again that it's picking up this organic signal that's deposited along this topography or impression of the tissue. And so in the next talk today, Hadeesha is going to share with you how you might use our lab's pipelines for modifying the noodle channel and its coefficients for your particular applications. But here I'll show you an example of our Rosetta Matrix 1.0, where here all of the various sources of contaminating signal are along the rows, and the different mass channels that might be included in your particular antibody panel are shown along the columns. Now, at first glance, this matrix might make it seem that there's a significant amount of contaminating signal that occurs in our data. However, it's important to keep in mind that the main sources of background are really coming from gold and organic signal, and that the remaining contributions here, whether they be impurities or elemental contaminations are occurring in very, very small quantities, which means that the coefficients of subtraction here are often very small. And so I'll finish my talk today by coming back to where I started, with this raw imaging data that has been subjected to no processing. I chose to show these three channels not only because they cover a wide range of the mass spectra, but also because these represent three very different tasks when it comes to image compensation. In the case of CD45, we can see that for the most part, this imaging data is already quite clean and has much more negligible appearance of noise or background. However, if we look at calprotectin, this antibody is in mass channel 69, which has incredibly strong presence of both gold and organic background. On the other hand, here we have CD3 epsilon, and this marker in general is quite dim, which means that in many cases, as you can see in the inset here, it can be difficult to distinguish true signal from noise. And so in this sense, while the first image here makes for a very easy compensation task, these other two can prove to be quite difficult. And with previous approaches, this would require us to do quite a bit of fine-tuning or customization of our parameters to make sure that we're accounting for all noise and background while keeping our signal intact. However, here, when I processed these images, I took our Rosetta matrix and applied it in just a single rapid step to produce the resulting images here. And what I hope you can appreciate is that in all three of these cases, we were able to achieve incredibly clean data that maximizes the true signal that is coming from biological staining. And so next, I'll hand it over to Hadeesha, who will walk you through examples of how you might fine-tune the Rosetta matrix for your own applications.
Great, thanks, Erin. Any questions for Erin, who will be answering through my voice? Okay, could you expand on the difference between adducts due to hydrogen and organic background also due to hydrogen? So the adducts are specifically occur when you have a hydrogen that arrives at the same time because it's been bound to one of the elements that were actually conjugated on the panel. So this is like, you know, a metal isotope that we put in there that now has either an oxygen or hydrogen coming along with it. So it's going to be directly proportional to the signal of the element that it's been bound to. The organics do not have any contribution from the elements that we've actually put on the sample. And so this is just, you know, something inherent about the tissue itself. So it's going to be all organic components, whereas the adducts are, you know, a proportion of the true signal that now is going to be contaminating a +1 or a +16 base. Could you please expand on ion pileup and wraparound? Okay, so this gets into kind of a more technical aspect of how the mass spec actually works, but essentially this is when a ion takes so long to get to the detector that rather than arriving where we think it should in the individual cycle of the top that it should, it like arrives in the next one. So it's almost like it becomes so late arriving that it's actually early in the next top cycle, and so it's off in where we would expect it to be, and so it gets registered as a much lower mass rather than a higher one. And so this causes a lot of confusion because there's no way to actually tell once that happens that it is due to a previous cycle, and so it will show up in an image where really it shouldn't.
No, how frequent is that?
Not very much. On the commercial instrument, I'd say that like wraparound actually doesn't happen a whole lot because there's a part of the secondary ion optics that sort of prevents these heavier things from getting into the top. So I think with earlier instruments, you might have seen it more, but with the commercial instruments, there's really not much of it happening.
Okay, someone said Rosetta V1 question mark. What's gonna cause it to be updated version? What will this come from? I think one of the big things for us is just seeing how representative the coefficients we picked are for other MIBI sites. We have now, this version 1 has been tested on 2 different instruments with 3 different cohorts, which is better than 1 and 1, but is less than, 20 on 20. And so really the goal is to try and figure out, get a better sense of how much variation there is across different MIBI sites, different MIBIs. And then a subsequent one would be sort of more of a consensus based on what everyone else finds, so that each individual site has to have fewer, and eventually the goal is no changes to the base matrix. Right now, this is the one that we've settled on, but we will sort of incorporate feedback from other people and either arrive at a consensus or maybe have like a couple different versions if we find some underlying factors that influence what degree of change needs to be made. The goal obviously would be, it's just a matrix that never changes. That's true, it seems, for everything except the noodle. So maybe there's something else we can do to more standardize on the experimental side what's causing the noodle contribution, or the instrument side, and then it would be a single coefficient. But right now it's kind of a big unknown, since it's a couple of our the other sites have started using it, but not systematically. Does the processing differ according to tissue density, tissues with holes, lots of cells? So one thing that we have found is that a major location where noodles can come up is at the edges of tissue. And so tissues that have more holes, you're gonna have more gold signal for sure. And sometimes noodles can interact with, because of the way the noodle channel is put together, it also has gold signal in it. And so there can be sort of a little bit of an overlap there. So definitely sometimes tissues with lots of holes will require different coefficients. But this is all stuff that is sort of still being explored, exactly what changes and when.
Yeah, and to clarify on that point, I mean, I think though, in cases what they're asking is that the process is the same, no matter what tissue it is, how dense it is, all that kind of stuff. I think the point that Noah's saying, and Hadeesha will go into this, is that the one variable, so pretty much the entire matrix, we don't think, pretty much none of it should have to be adjusted, with the exception of a potential change in the weight of the noodle coefficients. And Hadeesha is going to talk about that here, but everything else should sort of be constant in principle across all the sites. Now, obviously, if people come back and using this, they're like, it's not working, then we'll revisit it. But everything that we've seen so far, and also from sort of a first principle standpoint, says that really the only variability could potentially be the magnitude of compensation for the organics with the noodle channel.
Okay, last question. Which markers are more prone to ion pileup in noodles? Does this differ between FFPE and non-FFPE? So we've only looked at this in FFPE, so not sure about what fresh frozen would look like. Data to have a clear idea of if certain tissue types have higher and lower noodle composition, because every time we have a new tissue type, everything about it is different. Also the panel is different, also the instrument so far is different. So that's something that maybe will come out with more people using it. But right now, it seems like there's small amounts of differences between every condition. So yeah.
In case, anybody cares, those differences, if I had to guess, are probably most likely attributable to the differences between tissue sections and tissues, and sort of the amount of salt that stays on the surface, and kind of where it where it tends to accumulate. And so that's probably where like the variation in organic intensity is originating. And so that could be an avenue in the future for maybe modifying some of the buffers. So we played around with some of this in the past of trying to, not much, yeah, but so there's avenues down there that people have used, like in just regular, like multi-imaging to remove, salt ions and replace them with, like, what do they use? These ammonium
formate or
Ammonium.
yeah.
So that's something we can maybe explore, and we'll, of course, if we find anything there that seems to improve things, we'll definitely post the protocols.
Cool. All right, next up, we have Hadeesha, who will be walking us through how you too can realize benefits of Rosetta.
Woo! Woo!
Yes.
As the virtual Erin said, I will be doing the second part of the session where we'll be looking at how to evaluate some of the Rosetta compensated images. And I think you'll hear me echoing a lot of the sort of thoughts and answers that were given on the questions for the first part. So let's get into it. So like Noah mentioned, this compensation matrix has now been run over 100 cohorts, including from our lab as collaborators, the explosive cohort, the neuroblastoma, the triple negative breast cancer, or the TNBC cohort, the ductal carcinoma in situ, or DCIS, and then the glial tumor cohort. So by bringing all these cohorts through the compensation pipeline, we've kind of dialed in these coefficients as we've heard. And we're at this point very confident with a lot of these coefficients, especially when it comes to a lot of the sort of metal impurities, as well as some of the adducts like the oxygen, the nitrogen, carbon, that gets attached to these metals that you've heard know expand a little bit of. But as Mike mentioned, and as Erin mentioned as well, majority of sort of the noise and the variability that we subtract in this compensation matrix really comes from the neural channel, which is from the 117 to 125 matrix. And again, as Mike was mentioning during the question session, a lot of the variability from cohort to cohort can potentially come from the neural channel because of certain things like the buffers used, how much salt is retained in different parts of the tissues, the different tissue compositions, and so on. So we think there might be some benefit to really having the option to just to adjust the coefficients on the neural channel, while keeping all the other those source channels that contribute to the background constant. Right. So that being said, again, I just want to emphasize that the default coefficients that we have sort of honed in on or dialed in really works well across a lot of these cohorts. But when you do, want to have the option of changing the neural or the organic composition, we do recommend to use sort of the same multiplier for the neural coefficient across all channels. So we would be changing channel-specific coefficients. Now, because the coefficients have been dialed in quite well, we'll start with sort of applying a multiplier with a very narrow range. So in this case, 0.5 and 2. And I'll show a bunch of images where you can see how the compensation works, or how the images look after compensation with the default multiplier.
Just gonna reshare because the audio is not good. I think it's Erin's. Erin's audio is overriding.
Awesome. All right, so yeah, I'm going to show you some images where we've done the compensation with the default coefficients as well as these multipliers of 0.5 and 2. Now, if you want to adjust these coefficients, I'm going to point to the Rosetta compensation notebook as part of the copy repo that Noah mentioned in the beginning. And if you have any questions on how to run your data set or how to operate this notebook, the computational team will be here for the Q&A after lunch today. All right, so I'll be using the DCIS or the ductal carcinoma in situ cohort as an example here to show you some of the channels from there. And I've selected sort of channels that represent low noise, moderate noise, and sort of higher background noise, just to show you how the different coefficients or the different multipliers of the neural channel affect the background removal. All right, so before getting into any of the specific channels, the notebook when you're doing the compensation, you have the option of testing a few FOVs rather than running the full compensation matrix on your full cohort, because your cohort might be hundreds of FOVs, and this is somewhat computation intensive, which could take some time. So the notebook will sort of auto pull random FOVs that you select, and we generally suggest to check the compensation on about 10 to 20 images. But in this case, I've stitched together 5 images just for the space. So what you see here going across is different FOVs. So every column represents a different FOV, and the rows here, the first row represents the nodal channel for that FOV, and then you have the raw image, so the uncompensated image. So in this case, this would be Erin. And then you have the compensated images where you have different multipliers applied. And now again, the different multipliers here only apply to the nodal coefficient, and that multiplier applies to all nodal or the same nodal coefficient across all the channels. And the multiplier of 1 is the default coefficient. So you can see just visually, just looking at this, the raw image, this is one of the examples of very low noise to start with. And with the multipliers, you can see that this is bringing the image up. And just looking a little bit more in detail, this is an inset, you can see how the different multipliers are forming. And with the 0.5, you can still see some of the background noise is there. And when you go to the multiplier of 2, and I pointed this out with the red arrow there, you can actually see a little bit of loss of signal. And in this case, the default multiplier, I think, is doing quite a good job of removing as much of the noise and the background signal as possible, while maintaining all of the real Erin signal. So the next example I have is SMA. So this is smooth muscle actin, and in these examples, it's mainly expressed in myocardial cells. And again, looking at different multipliers, you see that all 3 multipliers are removing a lot of the noise that's there, which is not a lot in this case. But what you see here that's different from the previous example that I showed you is that the SMA signal is so strong, so much stronger than the background signal, that all 3 multipliers are actually not removing any of the noise. Removing noise, but not removing any of the real signal. This is sort of be mindful of when looking at the image, if one of your signals are very weak and it's closer to the noise level, and one is very strong. The next example I'll show is FAP. So this is fibroblast activation protein, which is expressed in the tumor stroma. And again, low to moderate levels of background. And when looking at the different multipliers, you'll see that starting with 0.5, you see a lot of the background signal being removed. But at 0.5, you still see some of the noise that's still there. Well, when you go to a higher multiplier of the nodal channel, 2, you really start losing some signal. And you can see that with, again, the red arrow that's pointed to the top left corner of that inset. So another example here is FCAN. So this is highly expressed in the tumor cells in this example. And again, a little bit moderate background. And when you apply the different compensation coefficient, you can see the background signal being cleaned up. And here again, I'm going to sound like a broken record. 1 looks really good. It's like the default value, it seems to be working really well at this sort of this balance between removing as much of the background signal as possible while maintaining all the real signal. And here again, with the multiplier of 2, you can see how some of the signal is being lost. So next here is Momentin, again, so moderate background. And Momentin is expressed in the mesenchymal cells. And when again looking at insects, you see the same sort of story where 0.5 is removing a lot of the background signal, but it still has some compared to 1 where you have most of the background signal removed, while the real signal is maintained. All right, so this one is KRT15. So KRT15 is a structural protein that's expressed in progenitor cells. And here, in this case, you can see that all 3 multipliers are roughly doing the same job. 0.5 might have a little bit of more noise, but 1 and 2 seem to be doing very identical sort of job of removing the background signal while keeping the real signal. So this example is the 8, and this is one of the examples with really high background noise. You can see this is the raw image, and with all 3 multipliers applied, you can see a dramatic change in the image as really cleans up the data. And looking at a smaller inset here, like again, this is sort of the same story that you'll hear. And so you have in the raw image, you have all that noise that you see, and with 0.5, it's getting rid of that noise, but not to that extent that you want it to. And when you go to multiplier of 2, you can actually start seeing loss of signal, so the thickness of those like sort of signal around the membrane gets weakened. But with the multiplier of 1, it's doing a very good job of sort of balancing that up. So with all these sort of examples that I've shown, I hope you can sort of kind of appreciate how the default coefficient is working quite well, just out of the box. So this matrix that we applied to the DCIS cohort was straight from the matrix actually Noah you used for the TMDC. We made absolutely no adjustments. And just to show you that you could actually even for like the first pass, just to see how the default matrix looks. I think it's a very good idea before you start adjusting. And even the multiplier that we applied here is actually quite small. All right, so with that, I hope with these examples, you were able to see how the compensation work and how to sort of assess your image after you go through the compensation. And the one channel that we would recommend if you do need to alter it to change sort of how much background that you want to remove, that would be the Noodle channel. And as for the previous discussion, we are still collecting data from other sites to see if any of the other channels need to be adjusted. But from our experience so far, it seems that the Noodle channel is the most the candidate that might be be adjusted. That's cohort specific. All right, with that, thanks everyone.
My main question is when you're doing so the noodle adjustment, so you're showing us kind of like tissue or by like antibodies, so like you're not gonna like use it like all at once, you're just gonna have to go through like each tissue type and like edit it accordingly, or is it like you're gonna run the whole thing and then you're just gonna have to go back?
Right, so I think what you're saying is like, do you apply, you change the coefficients per FOV?
Yeah.
Or do you apply, no, so this would be, what we do is, so the matrix will be applied to your entire cohort.
Okay.
But before applying it to your whole cohort, like all the FOVs, you wanna test if the default multiplier, for example, is a good one to use for your cohort.
Okay.
So we'll stitch together like 5 or 10 or 20 FOVs from your cohort.
Okay.
And then you can check how the whole matrix applies to all those different FOVs. And those might be, because they'll be randomly selected, they'll probably represent sort of your whole data set by sort of, if it's like, FOVs that are closer to the layer slide, center of the tissue and all that, and you can evaluate if the single compensation matrix can be applied across all those tissues. And you want to find a balance when you're trying to adjust the noodle channel that, across all those FOVs, you're getting, the good background null, like keep the real nodes. That makes sense.
I think one thing to go by is that when you're trying to evaluate how well the default's doing, really, I think the thing that's probably the most efficient is start with the channels that have weaker signals. And I would say that's really what you want to guide, what the weight needs to be, because as the signal intensity, like on brighter channels, is a lot higher, some of those, honestly, I mean, in some cases, like might not even need any cleanup because the signals are so bright, right? So you really want to make your decision based on like what's needed for the weaker signals. Okay. And that should get you to the right place.
Like you can see that with the example with SMA where you have bright signal and all three coefficients do great job of moving the background, but nothing happens to the signal. So it's not as informative for you to pick out which coefficient you pick.
Is there a point where you would recommend like just changing that specific cell or whatever for like, hey, this is a really weak marker and I don't necessarily need to adjust my whole multiplier and I just need to adjust like this one coefficient? Or would you recommend strongly staying away from that?
I want to push this question to Mike.
So by the nature, so the magnitude of all of those coefficients can go up or down. But the one thing that we are pretty sure about at this point is that the proportions between them should be very consistent. So the reason I wouldn't do that is because, you know, is that really you should only have to increase or decrease the multiplier across the whole row. So the proportions of those adducts should really be constant relative to one another. So I would be concerned that if you selectively edit them, you're kind of, you know, you're kind of overfitting in a sense,
Yeah.
right? You're trying to do something that you're trying to take care of a problem that's not really being driven by the organic signal.
Okay, thank you.
Yeah, because the thing to remember is that the sources of the noise are not proportional to the strength of the signal in the channel that you're looking at, but the strength of where they're coming from. And so that's really what the coefficients are designed for.
Okay.
A couple people had questions about what they did. They noticed that the images look like smooth. So can you talk about why that step?
This is the Gaussian blurring.
Yes, exactly.
There's one example that I can show you, but maybe, you know, Noah, you could talk a little bit more on this, because I know you've done quite a bit on this front. Oh, how do you share the hidden ones?
You just click, you have to click on them and then interview. Like you're already there. Yeah, so a couple people commented on the fact that it's not just the noise that's being removed, but in the Rosetta process, but the images actually look a little smoother, like higher signal than noise. That's because we apply a very small Gaussian blur to the images prior to doing the Rosetta step. The reason we do that is to make sure that if there's, you know, both in the source images and in the target images, if there's what appears to be a 0 pixel, but it's surrounded by a bunch of non-zero pixels, chances are it actually isn't a true 0. And so we smooth it so that there's a better representation of what the signal actually looks like in that area, because then when we do the subtraction, nothing is getting missed. The other benefit of doing a Gaussian blur, is that it allows us to take the data which comes off the instrument, which is integer based, and convert it into a float. So what that means is that, you know, integers, for the non-computational people, there's kind of two ways of representing the underlying data. You can have it either be always integers, 1, 2, 3, 4, 5, or float, which allows you to have decimals. And so the advantage of having a decimal representation is that you can then take a proportional amount of the signal off of the image. So you can say, oh, I want to decrease this by 30% or 40%. It doesn't matter if it's a 2 or 3 or 5. It actually does decrease by exactly the proportion you want it to. And so the benefits of this is that the images look like a little bit more cleaned up. It helps automatically denoise some of the very thin signal, and it makes the coefficient subtraction more accurate. And so those are all the it also helps with some downstream things, because then you have more smooth distribution of count, which helps for thresholds and all these other things. So we've incorporated it into this part of the pipeline because of all of the sort of runoff benefits that it has.
Right. And you can see in this example, like on the raw image, you almost cannot see sort of cellular signal, or like membrane signal, but as soon as you sort of start moving it out and doing the background abstraction, you start seeing actual membrane signal.
Okay. So are there batch effects that you see for Rosetta across different slides?
Across different slides. I don't think we've observed that. So when we sample the random FOVs to evaluate how the default coefficients are working, so that they do get sampled across different slides, and we have not come across that.
Yeah, someone else actually had that exact question. How do you pick the representative FOV? So I think that's key. Built into the process. It will randomly sample these images from all of the runs you've done. And so if you have, like, using that, make sure that the coefficients you get really are representative of your full cohort. And if there was a potential batch effect, that's maybe where it would pop up. But in general, we I haven't seen a strong case where there's something super slide specific that would necessitate changing the coefficient just for that batch. How does tissue quality go to okay, great. Any other in-person questions? Yes.
This is kind of, how many FOBs do you take at a time? And like, how often do you run a molly or something in between to check?
So that's coming up.
Okay,
Did someone plant that question? Okay, that's our next talk, which is how we handle that. Okay, thanks, Hadeesha. Okay.
Don't you worry, you're gonna hear all about that now.
More than you ever wanted to know, probably. Okay, great. Thanks, everyone. So wrapping up this session on MIBI processing, I will be telling you about the approach that we have developed for accurately assessing the sensitivity of the MIBI instrument. Brief outline, I'll give a background on sort of what it means and how we think about separating technical variation from biological variation. I'll talk about the metric that we have put together called median pulse height that we think does a really good job of specifically isolating the technical variation on the MIBI instrument. Talk about how we use MPH for calibrating the instrument, meaning performing the detector sweep, and how we can use MPH for normalizing our data after it's already been acquired. So what is the difference between biological and technical variation? If you think about your true biological signal, there might be different images or different, FOVs, different cores in your TMA that have true differences in the amount of signal for something you care about. However, there could also be, and we actually know this is the case across many different instruments, some sort of general technical influence where over time or over acquisition time, something is going to change. And so the result is that your true signal, which you know has this variation, gets basically multiplied by this decrease that is, or increase depending on the instrument that happens. And the result is that your true signal will sort of not be representative of the observed signal will not be representative of what you know the true biological signal is because of the confounding of this technical artifact. So the main source of this on MIBI instruments is the detector. And so what the detector on a MIBI scope is the thing that is actually registering and recording the ions as they physically impact it, after moving through the entire top. The reason that this is a source of technical variation is that those ions really are like hitting the detector. And so if you are acquiring lots of image data over an extended run, what's going to happen is that each impact from an ion on the detector is going to degrade it a little bit. And so over time, it will have a weaker and weaker output, even for the same amount of true incoming signal. So we were meeting last week and Mike was like, I know the perfect analogy for this. It's like an amplifier. I was like, okay, sure. So detectors are like amplifiers for ions. Why does this matter? You can think about changing the volume on your speaker, and the result is that it's going to increase or decrease what you hear in the output. The issue is that there's also baseline differences in the loudness of the music that's being played. And so you don't know for sure, did someone just crank up the volume, or is this song just really, really loud? And so this is the fundamental issue that comes up when you're trying to figure out an accurate way to assess the sensitivity of the instrument, is why is something loud? Is it meant to be loud, or it's because you've actually changed it to be loud? So what are some of the existing ways, previous approaches for assessing detector sensitivity, and why did they not really get the job done? Probably the most basic one you could think of is just measure some signal over the course of your run from your actual samples. So here's an example of the intensity in each FOV plotted for CD45. And what you can see is it looks different in different runs, different FOVs, sorry, within the run. The reason that we don't just look at them and say, wow, look at all those changes in detector sensitivity, is because intuitively, like, oh, well, obviously, CD45 is going to be differentially expressed in different samples. And so just looking at the sort of total CD45 signal, the intensity of the CD45 signal, the 99th percentile, any of these metrics you could think about, all of them are fundamentally confounded by the fact that either there's a change in cellular composition in your samples, or a change in marker intensity within those cells. All of these are interesting things that we care about measuring. The impact is going to be like, oh, CD45 changed. Another way you could think about measuring sensitivity is looking at some sort of control sample. And so on the MIBI instrument, this could be running a PMMA control slide. This could be doing a molybdenum control in between your runs. And this tries to get away from the fact that in your actual sample, stuff changes for a lot of reasons, to instead have a control standard that would account for this. The issue is that in order to get this information, you have to actually acquire this control sample. And the control sample is not part of your, the data you're looking at. This is something that gets added in after the fact. And so depending on how long it takes and how reliable you think the control is for your actual data, it doesn't sort of map exactly one-to-one with what does the sensitivity look like in the actual sample I'm looking at. The ideal for some sort of sensitivity metric would be something where you could just directly look at your images and know, here is the sensitivity at this time. And it wouldn't require you to run additional control samples, doing the PMMA, you have to actually do a slide exchange. There's all this like additional effort that goes into it for a readout that's less faithful than if we could find something that you could directly take just from the image data. Okay, so why do detectors decrease in sensitivity, and how does that actually manifest? The way detectors measure stuff is that when an individual ion hits the detector, it will produce something of a certain pulse height. This is what actually gets measured by the detector. Different ions will hit, they'll have pulses of different heights. What we do is set a threshold across the entire detector for every ion that says if it's above this level, count it as a true event. And if it's below this level, don't. This is basically noise. And this threshold gets set for the instrument, and then any pulse that's above the threshold counts as an ion, and any pulse that's below the threshold doesn't count as an ion. So what happens over time as the detector gets tired is that the pulses get shorter. And because the threshold is not changing, the end result is that the binarized outcome of is this above the threshold or is this below the threshold will become less sensitive over time, because the noise still is the same magnitude, but what we're seeing is that the true signal is sort of getting degraded because the detector has atrophy, basically. And so as you continue to run longer and longer and longer, for the same amount of true signal, those pulses will be shorter and shorter and shorter, and fewer of them will be over this critical threshold for counting as a true signal. The issue with all of the metrics we talked about up to this point is that they don't have a way of distinguishing between, are the pulses getting shorter, aka the detector is really decreasing in sensitivity, or there's just fewer things to measure in the image. So an example here is, let's say, this is the start of your run. There are 8 of these pulses that are over the threshold. And so what you would see on this simplified example is there would be a count of 8 for this channel in this image. However, let's say you had some different sample that was just sparse. There were fewer cells, the person designing the TMA missed the region they were supposed to be looking at, it's a very small biopsy, whatever the reason is, there's just less true positives. What this would look like in this, sort of low abundance sample, is that there would be fewer counts. But that's expected. Nothing needs to be corrected here. It's just a sample with less stuff in it. The issue is that if you actually do have a decrease in detector sensitivity and the pulses really do get lower, you're going to measure the same thing. Once you binarize them and looked at the output, you're like, oh, there's a count of 5 here. And looking only at the thresholded version of those two, there's no way of telling the difference between is it low because of counts, or is it low because of an actual decrease in sensitivity, or is it low because there's just not that many actual biological signals. So you probably with this, setup, you can see what we've decided is the actual way to measure this, which is we just directly look at the height of these pulses, and that should give us an intuitive way of understanding what the sensitivity of the detector is. So why does this work? You can think of 2 examples here. One where we have a lot of pulses, and the second one where we have not very many pulses. And so if we use a binary, some sort of thresholding, cutoff, whatever, we would have the same problem we had before, where we wouldn't know the difference between something with a small number of pulses and something with a large number of pulses. However, the median of this distribution is the same. It doesn't matter if there's a ton of signal or a tiny amount of signal. If we just calculate the median of the heights, not the binarized versions, but the pre-binarized versions before it gets thresholded, now we have a measure that tells us how sensitive is the detector that is independent of how many actual ions, images, etc. were acquired. Okay, so this is sort of the metric we're going to be using, MPH. Now, how do we actually use this to do the useful things we care about, which is determine, the health of the detector and how to potentially adjust our data. The first thing we do, and this whole process is laid out in the Toppy notebook, so we'll walk you through. He's using a detector sweep to generate a tuning curve. So we've identified a metric that we want to use. Now we have to sort of get a ground truth for what this metric looks like. So, the detector sweep is basically an automatic procedure to slowly increase the voltage and then measure the resulting output on a control sample in a controlled way, so you can get to understand the relationship between the current voltage and the output. What you can see here, and if you've ever looked at the output of the detector sweep, is that there's sort of diminishing returns for increasing the voltage. So initially, you'll see a large increase in total counts when you adjust the voltage. This is because the detector is getting more sensitive. The pulses are basically too low; they were under the threshold, and so changing the voltage makes the pulses get higher. But over time, this effect diminishes because once many of the pulses are above the threshold, making them even higher, it doesn't do anything. So this is why you don't want to just crank the detector voltage up all the way, because it doesn't actually help you get more signal. It's just going to take the noise and now start putting back over the threshold. However, what happens over time as detectors age is that they need to be at a higher voltage to get the same output. And so this is sort of what the process of tuning, tweaking, calibrating a detector looks like, is figuring out for that specific detector what voltage is going to give this optimal part of the curve. So this is a voltage versus total counts curve. But what we want is a tuning curve that's independent of the specific voltage, because we want to be able to use this for whatever the health of the detector is. So what we do is first calculate the median pulse height for each FOV. And then so that's the x-axis is going to become MPH instead of voltage. And instead of just the total counts, what we're going to plot it as is a proportion of the max. And so what we'll get is something like this, where previously you had 2 curves that were separated by voltage, but because the MPH is actually the same, we can then combine these into a single curve, which tells you for this MPH value, you're going to be at 60% of your maximum, or 80% of your maximum, or 90% of your maximum. And this is something that's now useful because it tells you how sensitive are you. Okay, so the first thing we use is basically to determine when the detector needs to be recalibrated or spiked. And so what you can see here is an example plot where we're plotting the MPH over the course of a run. Each dot here is the MPH of an individual FOV plotted in sequential order. And so this allows us to sort of monitor in real time. This is one of the applications we have of this, monitoring notebooks that we talked about, where we'll just tell you what's the detector look like from the actual data from your most recent FOV. So this is good because it allows us to say, okay, here's where the MPH is at this given time, and therefore with the tuning curve, here's where our sensitivity is. But it doesn't tell you how low is too low. How do you actually know when it's time to tune the detector? So what we've found, this is another thing where, with our two instruments, we have a range that we think is pretty solid, but as more people start using it, we will probably, narrow in on what the appropriate range is for many of the different MIBI sites. In our experience, an MPH between 5,000 and 6,000 usually is the lower limit of where you want to go before retuning the detector. And that's because this corresponds to about 50% of the max. And in our hands, if you're in the 50% to 100% range, the signals look dimmer, but you're not actually losing anything. Once you go below 50%, you start to actually lose signal, and then you can't, adjust for that later. The way that we figure out the specific threshold for where to, have like your cutoff point of like, okay, time to stop with the detector is with the following procedure. We basically will intentionally run the detector well below where we think the minimum is. And the reason we do this is so that we can plot over time what the signal looks like for each channel with the specific panel that you're planning on using. And the reason we do this is because depending on what titer you've chosen, depending on the intensity of the markers that you're looking at, it could be that you are much closer to starting to lose signal than another person. So what we do is this would be a good application of the dress rehearsal panel that Hadeesha talked about. Is once you've done the staining, you start at an MPH that you know is in the safe range, and you just do a long run going well below where you think would be healthy, and then you can actually stitch the image together and look at them and say, here's the point where it starts to get not just dim but like unusable, and you can go back and say, okay, this corresponds to an MPH of 5,400 or something, and then that's your internal benchmark for how far you're gonna run. There currently in our hands is not a super automated way of, once you know, okay, I want an MPH of 5,400 is gonna be my minimum. How do you set that? It's basically you look at that curve and you're like, okay, I think it's gonna give me about this much juice. And so this is something you just develop an intuition for as you use it more. The goal eventually is that this gets integrated directly into the commercial software and it is doing the adjustment and none of this has happened. But for now, this is the approach that we're taking. And why are we taking this approach? Because it allows us to do really long runs. Every time you have to stop the run, sweep the detector, reset up your points, it both slows you down, especially if it's happening at 1 a.m. That just means you lose the next 8 imaging hours. The other benefit is that if you can reduce the number of exchanges and stops and restarts, it reduces the number of opportunities for human error. And so if you're acquiring a lot of images, it is really advantageous to be able to just, single-mindedly, carefully check everything once and then run for a long time, rather than having to every 2 or 4 or 6 hours reset up your run. And so with this current framework, it's not perfect. There's a fair amount of sort of bespoke user intervention, but the result is actually much less user intervention once you started your run. And so for us, with these large cohorts that we've been talking about, it's a really good trade. And so as I mentioned, we have a notebook that will basically take care of all the details for you. It doesn't require much coding expertise. Once you set up Toffee, this is just baked into it. And you basically just say, here's the name of my run, here's what I want to measure, and it'll make those plots for you automatically. Okay, so once you have your image data, which now is somewhere between 50% and 100% of the max signal, what are you going to do with it? If that was the end of it, then you'd have a huge problem because you have a lot of batch effects in your data. You say, oh, it's look at all these differences, but now, depending on when your image was acquired, your bright marker would look 50% dimmer compared to the max. And so what we can do though is, because we know the relationship between MPH and signal, we can just directly use that to normalize the images. The process for that is first calculating the MPH for each mass in each FOV in a run. We then generate a fit over the course of the run for each of those masses. And so here's an example. It will look something like this. This is mass 156. On the y-axis is the MPH, and on the x-axis is the FOB number. And so what you can see is that there's this sort of general decrease in MPH over the course of the run. There's some amount of noise here with the points kind of bumping around. And so that's why we fit a curve to it to sort of remove any of that, a fair amount of that variation. And then this gives us a good estimate for each mass of what the MPH is. So what do we do with that information? We use that to figure out what the normalization constant should be. So as I mentioned before, we already constructed this MPH versus maximum signal intensity curve from doing the detector sweep. We only have to do that once. This is something that is intrinsic to the instrument. It just says, you know, this value of MPH, what fraction of the maximum does it correspond to? We then, for each run, for each FOB, for each mass, calculate this curve. So this is one that we redo every time. And this tells us, you know, for this FOB and this mass, what MPH do we estimate it to get? We then just plug in basically to say, okay, this mass is at this value. That's going to determine what the normalization constant is. So for example, we would look at, you know, FOB 14, say, we find where on the curve the fitted MPH value is, and say, okay, this is, you know, 5,000. We then plug in that value of the MPH to the normalization curve that we've derived and says, okay, this is 80% of your max signal. And then you just divide so that everything ends up being at 100% once your run is done. Okay, so here is an example of this in practice. So I'm showing on the left here, H3K27ME3, which is a histone mark. The top row is the first 3 images in the run, and the bottom row is the last 3 images in the run. And so this is a marker that has biological variation in it. It's not just total histone. We expect differences in methylation. What that means is it can be tricky to know, is a change that we're seeing due to actual biology, or is it because the sensitivity has gone down? And the nice thing about this normalization is it allows us to tease out those facts, and we can just run it and say, oh, okay, now these images are like sort of back at the true sensitivity. And so one thing you can see here is that the top row is basically not getting changed at all. These are all scaled exactly the same. And that's because it was at the start of the run where the sensitivity was already very close to 100%. Whereas the bottom ones, which were towards the end of the run, are getting materially changed. And the result is that everything kind of looks broadly similar, but there are still the biological differences that are being left in, which would not happen if you were doing some sort of, you know, overall pixel normalization where you want to bring everything to the same. On the left here is, right is C14, same story, before and after. You can see just this is, you know, an example of a different marker where it's selectively bringing up the dim images at the end of the run and is not modifying the already bright images at the start of the run. Now, what I've talked about here is a normalization method, but this is normalizing specifically for intensity changes due to changes in detector sensitivity. If there are other sources of variation or batch effects in your data, this approach is not going to normalize them out. The only thing this is good for is for detector sensitivity. So shown here is a large tiled image that our friends in the Knoll lab have generated. And what you can see is that there are significant sort of dark spots in the image. And this is something that we have observed when you're doing big tiled images that is not dependent on run acquisition order. So there's some other source of systematic sensitivity changes that are occurring specifically, we think, when you're doing large tiled images. And because it's not correlated with acquisition order and detector sensitivity, our approach does not resolve these issues. So they have started looking at other approaches, you know, some estimating kind of the true signal based on unchanging marker, some of the, you know, more similar to previous approaches, because it doesn't appear to be driven by detector sensitivity. This is something that we're kind of troubleshooting now, but just as a heads up, that if you start doing large tiled images, right now it appears that there's like some sort of systematic issue with the way the instruments are set up that results in these intensity changes. This is just an example. There could be other batch effects, for example, staining artifacts of, you know, messed up the concentration, you didn't follow Hadeesha and Ben's protocol for double checking and you edited the wrong amount. Those things are not going to be solved by MPH normalization. It's only going to account for the problems that are the MIBI's fault, not that are your fault. Okay, so summary, most methods to assess sensitivity can't distinguish between sparse signal and low sensitivity, which is sort of the crucial difference. Median pulse height that we've developed is independent of signal quantity, and it can be assessed directly from acquired images. It doesn't require any additional controls. We can use this both to determine when the detector needs to be calibrated to normalize images, and it's available as part of the topic package from our GitHub. And with that, I will take any questions. Thank you. Eric.
Yeah, I don't have a question. I just have a, a statement. So basically, in the next software release coming out 1.6, which should be available in the next couple of weeks, we are going to be providing a metric for the detector health after Umali QC based on this MPH, and it'll be a number that's basically 80% or 82% to 100%, 120% as the recommended range. If you drop below that, the calibration algorithm is a high probability of failing, then you'll be contacting IonPath to set your gain for you. So, I mean, we still recommend maintaining that like 80 to 120% range. But this would be like a post-processing way to sort of correct for the deviations outside of that in the detector gain. So,
Yes. Yes.
Does this have to be run simultaneously while collecting your data, or can it like pull this information from images that have already been collected?
Yeah, so all of the information for calculating MPH is contained within the bin files. So as long as you have the bin files, which are the direct outputs,
Yeah.
it won't work from the MIBI tips from the IonPath tracker because it needs the pre-unprocessed data. But as long as you have the bin files, you can always calculate this. Obviously, if you want to use it to determine when to calibrate the detector, you need to do it in real time. But if you're relying on IonPath for the detector calibration and just want to use this for normalization, then you can do it at any point.
one more thing.
Yes.
By the way, yesterday in the roadmap, I had a bullet on automated tuning. This is one of those. There's going to be a day, hopefully in the not too distant future, where the gain will just be maintained at optimal value automatically, essentially based on a lot of the underlying algorithms that Noah presented here, where they look at it manually and look for the optimal gain. We're working on doing it automatically. So hopefully detector gain becomes a thing of the past.
Is there another in-person question? Okay, to what degree does age of the detector influence MPH? So this is kind of the fundamental problem that we're dealing with. As the detector ages, the MPH decreases. And so that's why with whichever of these methods you're using, you have to be constantly calibrating the detector, because every time you smash it with more ions, it gets less sensitive. You have to increase the volume in order for it to work. So this is like basically the fundamental trade-off that is occurring. Okay, so we observe basically at UMN,
University of
Minnesota. Okay, they're saying they've picked up the same thing where you have tiled images, they're observing these differences that are independent of acquisition order. And so what do you do about that? How does that impact downstream analysis? I would say we haven't decided what we want to do about it yet. It's yet to be determined. By eye, visually, they look very annoying. I think the question is quantitatively, how big of an impact they have on downstream analysis. If it's substantial, meaning like something that would be called positive in one image is now being called negative in another because of the change, we will think about an additional normalization step that would be more ad hoc. But so far we haven't gone there yet. Obviously, the best case scenario is that we just figure out what in the instrument can be adjusted to remove this, but that would probably be a longer fix. So for now, stay tuned, and if we do decide to do this, it will show up in Toffee once we do.
So the thing I'll add on that is that I don't think it actually has anything to do with the instrument. It's probably something that's going to have to change with the sample prep. And so that was kind of the first thing. And the second thing is that I've been looking at this with Erin, and we're pretty sure. The good thing is if you acquire these fields in a random order, then you can actually just use the intensity from neighboring tiles to know how to add a second layer of normalization to kind of take care of these issues. And so we're going to be looking at that to see if we can implement it. And if we do, obviously it'll get posted to copy.
Should there be like a minimum number of tiles if you're doing a tiled image to prevent, like, if you're randomly acquiring like a 2x2, does it really matter if you're randomly acquiring because they're still all really close to each other?
2x2 probably doesn't matter. I mean, so I feel like randomizing your tiles in your runs, it's kind of like brushing your teeth. You should just always do it because it will never hurt. Right. And it's it's good to just to always do it and not have to think about it because it doesn't really cost you any extra time. Now, to your point, like, I mean, if it's a 2x2, no, I'm sure it doesn't really matter, but but I think, it's like another decision people don't have to make. So that's kind of like why I just tell people to always randomize their stuff.
Okay, so we had a question about basically how many FOVs does it take to get there? I think that's another big thing that changes over the lifetime of the detector. Initially, we're looking at maybe between 12 to 15 800 micron FOVs acquired at the course preset before we drop below this threshold. Once the detector is, sort of in like middle age, we can often go like 30 or 40 800 micron FOVs at course before needing to adjust if we're using our 50% cutoff. If you use the 80% one for 9.5, you will do it more quickly. But in general, it's like somewhere between very early on 12 hours up to 36 or 40 hours by the time the detector is very broken. Okay, how different are the MPH values for each channel? So, I mentioned that we do this step of fitting the MPH over the course of the run for each channel. The reason we do that is because the MPH, the relationship between MPH and total counts and proportion of maximum counts doesn't change. But at a given snapshot in the detector's life, different channels will be at different MPH values. And this has to do with like the, internal top mass spec stuff, but basically we'll sometimes notice, up to a 20% difference, I would say, in MPH for different masses. And so that's why we have this per mass step where we calculate what it is for each channel. And then we use that to normalize. So it's not a big deal. It's an open question if we even need to do this, but for now it's easy to do, so we're doing it. We may decide to just move back towards a single normalization constant for every channel in a given image, but for now we have this per mass normalization. Okay, Amar is raising their hand. Oh, wow. You have something you want to ask? Okay. If not. All right, well, with that, yes.
I just have a quick question. So relating to your discussion of like other sources of variation beyond like technical from the machine. So for example, like how well tissues are preserved during that initial fixation process. Is there like a method to potentially normalize based on that, or is that maybe not necessary?
Currently, no. I think it hasn't come up yet for us. I think probably for you guys, it won't come up since all of your tissues are perfectly preserved.
Yeah, but just like in other circumstances where like maybe clinical samples are not like preserved like immediately, or maybe there's some kind of like lag time.
There's been work to try to look at, David Rim's lab at Yale actually did some work about 10 years ago, looking to see if you could use, you got to identify sort of like bellwether housekeeping proteins to assess tissue preservation. And that's definitely something, like if the need arises, we could revisit. I think at this point, even in the clinical cohorts where we're looking at archival samples, I mean, I guess it's, I guess we don't know that does it appear that it's been a source of systematic bias? But if we start to see evidence that is an issue, I think that there are ways that we could, have internal standards that try to at least flag problematic samples, if not try to normalize it.
Yeah, because even in some like preliminary titrations of like some old samples and then going to like the specific like non-primate samples, there's a significant difference in like brightness and intensity. And so that's where I was wondering if that's something.
Yeah, the question with all this gets back, because we wouldn't have NPH as a readout, you would need some way of knowing the ground truth of how much had been impacted. Because you're gonna have samples that are dimmer just because biologically they're dimmer. And so you need some way of assessing it's not biologically the dimmer, but just truly, it's just the data quality is worse. Maybe if every single channel is dimmer, that would be a good insight that it's something like that. Maybe if the noodle is, someone just said, could you use noodle channel for this tile thing to try and figure out if it's just a global problem or a biology problem. If there was a marker that you felt really closely tracked only with sample quality, then it would be very straightforward to do the normalization. But in the absence of that, you have to make sort of a call of which signals only correlate or mostly correlate with quality and which of those could be dimmer, but also for other reasons, before you start normalizing out the actual true variation that's in your samples.
Yeah.
Cool, thanks everyone.